As Jan said, my name is Camille, and I'm part of the CMET research group of Ghent University. And today I'm going to present results from my first year of PhD that we published last year in Green Chemistry, which is about the production of isobutyric acid from methanol by Clostridium luticellarii. So you might be wondering how methanol fermentation could be related to the let's say, capture platform. It is in a sense that methanol has been proposed in recent years as a platform chemical for carbon capture utilization. Indeed, methanol can be produced catalytically by catalytic hydrogenation of CO2 with hydrogen. And in the context of carbon capture, ideally the CO2 would be coming either from industrial off-gases or directly captured from the air. And the hydrogen used for hydrogenation would be generated using renewable electricity sources. Then this methanol can be upgraded into a set of different chemicals or fuels by chemical processes, electrochemical processes, or biotechnological processes. And what I'm presenting today is an example of a methanol upgrading biotechnological process. So what does it rely on? It's related to anaerobic methanol fermentation. So some acetogens, which are, if people don't know what acetogens are, it's bacteria, anaerobic bacteria that are able to grow on CO2 with the electron acceptor, which is traditionally hydrogen. And most of them produce acetate, but the key metabolic point in acetogens is their central compound in the metabolism is acetyl-CoA. But some of the acetogens are also able to grow on different electron donors and different electron acceptors, and some of them were able to grow on methanol, which is what I'm interested in. When we take a look at the product spectrum of those methyl-trophic acetogens, usually they produce mainly acetic and butyric acid, but some of them were also able to produce longer chain carboxylic acid, valyric and caproic acid. But until recently, it was always limited the product spectrum to straight chain carboxylic acid. But this changed in 2017, where in a mixed culture continuous reactor that was fed with methanol, acetate, and butyrate during the last operating phase, they observed a high isobutyric acid production that had never been observed in any biotechnological process. And they hypothesized that isobutyric acid was produced via bioisomerization of butyric acids. But what is a little bit tricky is the fact that if it is indeed produced through bioisomerization, this reaction doesn't bring any energy, so it's hard to understand why this compound would accumulate in the process. So the objective that I had in my research was from a similar methanol fermenting mixed community to isolate and identify the organism that is responsible for isobutyric acid production, to explore whether or not it could produce other isocarboxylic acid, and then to screen and characterize conditions that would enhance isobutyric acid production. So, like I've just mentioned, the first task was isolation. And so what I did is I run an isolation campaign from a mixed culture reactor that we had running that was producing isobutyric acid from methanol. And I run that isolation campaign by performing plating isolation techniques on two medium, a rich medium, so reinforced Clostridium medium, and a synthetic medium that was the same as the one used for the mixed culture reactor for feeding the mixed culture reactor. And what you can see is after plating, I transferred all the isolates I obtained on the different medium back to the synthetic medium in Hungate tubes to test their product profile when growing on methanol and acetate, and CO2 as well. And what you can see is on the left bar chart is the product spectrum of the isolates obtained on the rich medium, and on the right, the one obtained on the synthetic medium. And when we take a look at those two graphs, we can separate all the isolates into two groups. One that did produce isobutyric acid with the butyric and caproic acid as co-products, and then the others that produce mainly butyric acid as the main product and sometimes traces of caproic acid along the way. Then after testing those the product spectrum, I sent all the isolates for 16S sequencing to figure out who was doing what and if different organisms were able to produce isobutyric acid. But the results came in, and all the isolates that were able to produce isobutyric acid were all related to the same organism, which is Clostridium luticellarii, which is an organism that has been isolated really recently in 2015. And until today, the only thing that was known about it was the fact that when it was growing on RCM, the rich medium I use for isolation, it was able to produce butyric acid. It had never been grown on methanol or CO2 hydrogen, and never been shown to produce isobutyric acid. And for all the other isolates, they were also all related to the same organism, which is a Bacterium limosum, which is an acetogen. That is the one that when I mentioned that some of them were able to produce longer chain carboxylic acid when growing on methanol. It is the one that is able to do it. So now we were at a point where we had an organism isolated, where there were isolates that were related to an organism that we know nothing about. So what we did is we ordered that culture to test whether or not our isolates were a different strain of the same organism that showed a different phenotype that was specific for isobutyric acid production, or if the wild type strain that was isolated in 2015 was also able to do it. So we ordered that the wild type, grew it on methanol and acetate, but we wanted to also screen different carbon sources to see if it was able to produce isobutyric acid, if it could do it on the other carbon sources. And in this results, you can clearly see that it did produce isobutyric acid also when growing on methanol and acetate. Interestingly, it showed isobutyric acid production on CO2 hydrogen as well, which we were kind of expecting because of the fact that it uses the same metabolic pathway as the one when growing on methanol as an acetogen. But then for all the other carbon sources, isobutyric acid production was not detected, and actually propionic acid and acetic acid were the main products. So after screening different carbon sources to test for isobutyric acid production, we wanted to see if it could produce different isocarboxylic acids. So what we did is we grew the wild type on methanol in combination with a set of different organic acid as electron acceptors. So we grew it on ethanol up to caprate, and then a couple conditions with the 2 carboxylic acids, so either even or odd chain in combinations. So from those results, the first thing that we concluded is the fact that it did not produce other isocarboxylic acid, or at least not in the condition that we run. It did produce, again, isobutyric acid on methanol acetate, and we already had a glimpse that providing butyric acid increased isobutyric acid production and selectivity. But one thing that we can see is that, similarly to Bacterium limosum, luticellarii is also able to produce longer chain carboxylic acid. So we see caproic acid production when we have even chain carboxylic acid that are provided, and we see valeric acid production when we have odd chain that are provided. after testing for, let's say, the metabolic capacity of luticellarii, we wanted to investigate the effect of pH on isobutyric acid production. Because when isobutyric acid production was first detected, it was hypothesized that the reason why the mixed culture was producing isobutyric acid was as a detoxification mechanism. So we wanted to see if by lowering the pH, it would result in higher selectivity and higher production of isobutyric acid under the same conditions. So we grew the wild type on methanol, acetate, and butyrate. And we grew this experiments on a pH range of 5 to 7. And what we could see is already that at really low pH, the growth was inhibited, so lower than 5.5. And otherwise, for the rest of the range, the culture grew, but the ideal pH was around 6.5. Then in terms of isobutyric acid production, the highest concentration was obtained at the ideal pH for growth, so which was 6.5, with the production of about 4.5 grams per liter. But when we take a look at the bar chart on the left, when we take that pH as a reference, if we go lower or higher, what we can see is there is a lower final concentration, but selectivity increases. The fact that selectivity increased with lowering pH goes well with the detoxification hypothesis, but we see the same effect when we increase the pH, which increasing the pH doesn't go well at all with the detoxification. The same increase doesn't go well at all with the detoxification hypothesis, because increasing the pH lowers toxicity of a carboxylic acid in the medium. So it seemed that the detoxification route is not or at least not the only reason why it was happening in the mixed culture. Finally, we wanted to see the effect of, we had seen that supplementing acetic and butyric acid increased isobutyric acid production, but we had no idea on when it happened. So we did a time series experiment where we sampled our experiments along 15 days to see how isobutyric acid production would occur and other products as well. And what the main point that we're interested in is the fact that when going only on methanol and CO2, isobutyric acid production only started after 7 days, and this coincided with the switch from acetic acid production to acetic acid consumption. When acetate and butyrate were supplemented, isobutyric acid production started from the start, right at the beginning of the batch, no matter what the butyric acid concentration was. This also doesn't go well with the detoxification mechanism, meaning that no matter what the butyric acid concentration is, this is not the trigger for isobutyric acid production. Supplementing acetic acid is one, and apparently isobutyric acid production is related to acetic acid consumption, as we can see on the methanol CO2 condition only. So to wrap up the key points of my work, they were that Clostridium luticellarii is the organism responsible for isobutyric acid production. It does it from C1 carbon sources, so methanol, and also we saw a glimpse of the potential to do it on CO2 and hydrogen. It can also perform C2 unit elongation to produce longer chain carboxylic acids. pH of 6.5 was ideal for growth as well as isobutyric acid production. And we could see that acetic and butyric acid supplementation enhance isobutyric acid production. And that was the end of my presentation. If you have any question about my work, you can just shoot, and I thank you for listening.